This is a discussion with Dr Fiona Beck, a fellow and senior lecturer at the Australian National University. She currently holds a Discovery Early Career Researcher Award from the Australian Research Council, as well as the Future Engineering Research Leader Fellowship from the ANU. She leads a research group focused on integrating nanophotonics and optoelectronic device design for applications in solar fuels and the next generation of photodetection technologies. I really enjoyed our chat. She was so approachable, and we talked a host of subjects from plasmonics to encouraging diversity within physics. I found it fascinating, and I hope you do too. Enjoy. So looking back at your early days, what inspired you to study physics and eventually go on to pursue your current field?
It's a good question. I've always liked understanding how things work, so that was a big driver for me. But I also think that I have a strong desire to make a positive impact. And I actually grew up in Botswana in Southern Africa. My parents emigrated out there when I was quite young. And it's a country with a lot of sun, a lot of space. And, I could see this, and also a very fragile ecosystem, actually. So it's semi-desert. And I became kind of clued on to climate change early on. And in my early teens, actually, was when the first time I actually started reading about it. And I became quite interested in this idea that you could use the sun as this limitless energy source. And in Botswana, when you stand outside in the sun, you can really feel the energy. So it was really driven home to me that this was a really important way to go. So I'm one of these very rare people that decided, when I was 13, 14, that I wanted to study solar energy and actually ended up doing it. Yeah. Okay,
so it was always a very clear path for you. And so even within physics, was there anything else that sort of interested you, or was it very, very much, it was always going to be solar energy?
Well, when I started learning physics at high school, I was just fascinated by everything, actually. I really enjoyed the idea of understanding how things worked. So even just thinking about how you could explain how things fly, for example, and understanding that there are laws behind that, and that we could actually work out how it all works. It was quite exciting to me. When I started university, I kind of started specializing more, but initially I just really liked, I had a real curiosity for understanding how things worked.
Yeah, I agree with that. It's exciting. It's very exciting learning about such fundamental sorts of things that you see every day. So jumping ahead a bit to your research now, firstly, how would you explain your research to an audience that don't necessarily all have PhDs in physics, but are eager to understand how you're going about looking at ways to convert light to other forms of energy?
Yeah, so I actually have three distinct research areas. This is kind of how I've organized my career at this point. So I started out my studies looking at solar cells. So how to make solar cells absorb more light. So at this point of time, which was around 2008, the price of silicon was really, really high. So solar cells, which are primarily made out of silicon, were getting thinner. And we were trying to figure out how thin you could go while still absorbing a lot of light. So the more light you absorb, the more energy you can get out. And interestingly enough, we started looking at what we call plasmonics. So plasmonics is essentially the root of the word is the same as plasma, right? So it's all these charged particles moving around. And in plasmonics, the charged particles are the free electrons in metals. So in metals, you have a whole bunch of electrons that are not strongly attached to anything, and they can react really quickly to any incident light, which has an oscillating electric field associated with it, right? So it's going up and down, as that's what light is. So this is why metals are shiny, right? Because you shine light at it and the electrons move and reflects, essentially the light is reflected back because it can't penetrate inside the metal very far. But if you make metals really, really small, like smaller than the wavelength of light, then really strange things start happening. And this is essentially the field of plasmonics. And then you still have your moving electrons, but instead of being able to move completely to follow the electric field as it goes in and out, as the light comes in, it essentially hits the wall of whatever structure it's in. The structure is so small that it gets confined. And when this happens, you can get really strong standing fields. So the way that the electrons move and the electric fields that they're generating and the initial electric fields of the light can all multiply up, and you can get nanostructures that look like they're blue or red or green, even though they're made of gold, which we all know is like this, is gold colored and shiny, right? So you start getting these really interesting optical properties. And one of the things you can do is, because it's determined by the size of the nanostructure, if you start playing with that nanostructure, making it long and thin or spiky, you can actually change where in the spectrum you get these strange resonances. So at what color light you're reacting most strongly, but also what happens to the light. So you can make it scatter, or you can make it absorb in this tiny nanoparticle. And we were looking at ways of essentially getting the light, collecting the light, and then scattering it back into the solar cell to get these really stronger amount of absorption in the solar cell. So that was a really amazing project. And I really liked that because I was able to use my fascination with optics and nanostructures to do this really cool thing in solar energy, which I was really passionate about. So that's sort of the first area that I worked in. And then the solar industry, as you might know, since 2008, has really taken off. They essentially solved the issue with scarcity with silicon, and the cost of solar energy has plummeted. And essentially, I feel that there is not a lot of basic research, or shall I say novel research, that needs to go into solar cells anymore. I think that there's still some development to be done, but it's more around materials, and it's more around the engineering and how you actually plug these solar cells into the grid. So I, very happily moved on, thinking that I could use my knowledge a little bit somewhere else. So that led me to what we call solar fuels. So solar fuels is essentially using this energy of the sun, so all the photons, the little quanta of energy associated with light, and instead of converting those quanta to electrons that are collected in a circuit, which is power, which is what solar electricity is, you take those electrons and you can use them to run reactions, which is really interesting. And if I can just sidebar very quickly, I am now working in this area, which we sometimes call it solar chemistry or photocatalysis. Sorry, photocatalysis. I should be able to say that properly. But I actually stopped studying chemistry in high school, right? So I've over the last 3-4 years, I've been able to transition into learning more about chemistry and the chemistry I need. And this is one of the wonderful things about being a researcher, right? Is you can move field and pick up knowledge, and you don't need to be stuck in, your narrow confines of any field. So just to say that, it's quite amazing what you can do with a physics degree.
Is it very different learning about things to do a project rather than learning about it just within the normal academic setting, as in a school or something?
Yeah, well, the nice thing about learning things when you're at high school or university is that someone packages it up for you and explains it to you. There's an active, there's someone who's putting in a lot of intellectual energy to teach it to you in a way that's clear. And there's someone there to ask, right? When you're learning these things yourself, you have to kind of do that yourself. You kind of have to set your own curriculum and decide what's important and what's not important before you actually know enough about the subject. So it can actually be harder to teach things to yourself, but at the same time, you can do what I like to think of as, just in time learning, right? So, at a point in my research when I need to understand what a redox reaction is, I can pause and go and read about redox reactions. And once if you go out to read something or learn something with a very specific goal in mind, like I need to know this for this experiment, then it is actually, it's a kind of different way of learning. You sort of are, you kind of know exactly what you're looking for, and it's easier to pick that up. So there's pros and cons. I enjoy both, actually. Occasionally I get to go on courses, usually about teaching or policy or something that's slightly outside my scope. And I really enjoy being a student these days. I really appreciate someone telling me what I need to know. So I do enjoy both ways, right? Yeah. But I apologize, I do tend to go on these tangents. So now I've kind of lost my thread, but coming back to solar fuels. So what we're doing now is we're using devices that look very much like traditional solar cells, but instead, once you get the electron, instead of turning it into electrical power, we then put it onto, we send it to some electrodes or some catalysts, which are essentially materials that make it easier for reactions to happen or more favorable. And we're splitting water. So we're providing the energy and the current or the electrons that you need to split the water molecule into oxygen and hydrogen. And that means that you have this energy of the sun is now stored in these chemical bonds. So usually we can sell the oxygen for medical uses or something like that, or even just let it go into the atmosphere. But the hydrogen is what's really valuable. And at a later date, you can get that energy back by recombining the hydrogen with the oxygen. Or you can actually use hydrogen for a lot of really important applications. So I didn't know this before I started doing this work, but we use a lot of hydrogen already. The most important thing we use hydrogen for is to make ammonia. And ammonia is the basis fertilizer. So essentially, the critical reaction that was developed by Haber-Bosch and allowed us to start feeding all the humans on Earth more consistently and with the resources we have is really a reaction that combines hydrogen and nitrogen, and that hydrogen is a really critical element to that. So by making these fuels with sunlight, we can really start looking at cutting the dependence on fossil fuels of things other than just electricity. So at the moment, when you want to make hydrogen, you take methane, which is natural gas, or you can use coal as well in a process called coal gasification. So in this way, you essentially get rid of the carbon molecules and everything else, and you're left with the hydrogen molecules. But those carbon molecules that are associated with all the organics in fossil fuels end up making a lot of carbon dioxide. So I think I've heard it said that if the ammonia industry was a country, it would be top 3 emitters in the world, right? This is a significant amount of emissions associated with these processes. So, using sunlight in this way you can actually start going beyond just decarbonizing electricity to decarbonizing industry, and potentially even fuels for things like airplanes and things that are much harder to provide energy for via electricity. So that's kind of where I am now. And because of my interest in solar fuels, I've kind of ended up going into other directions. So on one end, I can't let go of my love of plasmonics and everything nano, and understanding those basic interactions between matter and light. So we're also looking at how you can drive these reactions in much simpler structures that don't require all the solar cell type architecture, and looking at what we call plasmonically driven photocatalysis. So these are looking at really complex self-assembled metal structures that can drive reactions just by shining light on them. And one of the reactions we're looking at is actually splitting carbon dioxide from the air to see if we can make something useful with it while reducing carbon dioxide. So that's a really interesting, very fundamental science project. And then on the other end of the scale, I have this involvement in this fantastic transdisciplinary project called Zero Carbon Energy for the Asia Pacific. And I'm running the hydrogen project and working with economists and lawyers and policy experts, and trying to figure out how you remake the energy sector in Australia in order to stop exporting coal and gas, which we do a lot of, and then instead export hydrogen and hydrogen fuels. So kind of going from thinking about what electrons and photons are going to co-authoring papers about policy. And it's really, I love the diversity, though it can be quite challenging.
Where do the problems lie in policy at the moment, and what needs to be done to ensure that we can effectively transition to a sustainable future?
I think one of the biggest ones is understanding how to regulate the trade of these new zero carbon fuels. So the issue is that, as I said, you can make hydrogen from gas and coal, or you can make it with renewable energy. And if you were buying a liter of liquid hydrogen, there's nothing you can do. You can't look at your hydrogen and know where it came from, right? So the economists call this an asymmetry of information between the buyer and the seller, right? Which is just a really long way of saying, like, we want to, if you can't necessarily just rely on trust, then how do you provide structures that allow your buyers to trust where that hydrogen is coming from? So what the basis of this is what we call certification. So we're actually, as consumers, we're kind of used to certification. Fair trade is a certificate. You see that stamped on coffee and chocolate, and that the growers of those goods have been paid fairly. So we're looking at the complexity of how you actually certify hydrogen, and under what circumstances that should be certified, and should you put a label on it like fair trade, or should you be saying, okay, this hydrogen has X amount of greenhouse gases associated with its production, and all the complexity of that. One piece of work we did recently was around making ammonia in Australia and sending that to Japan, because Japan are really dependent on coal-fired power stations. And what they want to do in the short term is reduce the amount of coal they're using by adding a little bit of ammonia into the mix. And you can actually burn that with coal to provide extra energy, but there's no carbon in ammonia, so less carbon dioxide. So what we looked at was, if you want to do this, so it turns out you can do this, about 20% of the energy in a coal-fired power station can be supplied by ammonia with minor retrofitting. You don't need to change much. But so we worked out how much carbon dioxide that would save in Japan. And then we did the sums for what the carbon dioxide would be released in Australia if you made the ammonia in different ways, from coal, from gas, from renewable energy, using some carbon capture and storage, all sorts of different methods. And it was actually quite interesting. So it turned out that the amount that you saved in Japan was almost exactly the same as the amount you released in Australia, if you make it with gas, without any, without trying to change anything. So essentially, this could become a trade in emissions. So, essentially, Japan's buying ammonia and you're doing all these fancy things and shipping it over. And at the end of the day, the emissions are moving from Japan to Australia, and Japan gets to, lower its emissions and write to the IPCC and say, look how great we are. And Australia, if Australia doesn't really care about increasing its emissions, then there's no net benefit to the world, even though we're all trying desperately to do these new fancy things. So it's really important to actually get the certification right and understand this. And one of the complexities is that, unlike other fuels, zero carbon fuels don't produce emissions at point of use, but they can have emissions when you make them, depending on how you make them. So that's one of the things we're working on and thinking about. And some of the things we're sort of recognizing, it's very complicated how you actually think about this. And as a physicist, it's really interesting to realize that a lot of the complex questions are not technical questions. We know how to do this technically, but it's around understanding how to regulate these things as well.
Okay. So going back, so talked about policy, going to your research, in terms of the technical side, how much time do you spend in a lab versus doing things theoretically? I'm now at the stage where I sort of manage researchers in the sense that I supervise postdocs and research fellows and students. So I don't actually get to do a lot myself, unfortunately, which I still enjoy, actually. There's still a lot of intellectual input that you can have as a supervisor. But when I was a research fellow, spending most of my time on research, I would say it was about, earlier on in my career, it was about 60% in the lab, 40% theoretical. And that's kind of switched because I actually enjoy the theory side quite a lot. So I'm particularly like making relatively simple analytical models that can tell you a lot about a system. For example, we wrote a model for our solar hydrogen generator using the solar cell that allowed us to sort of turn the knobs of the material properties of the semiconductor and the catalysts and everything and work out what the maximum efficiencies were and what things you could change that would really affect the efficiency, for example. And that then, using that, we were then able to really design the best kind of cells, the best kind of devices, without having to run a million experiments, right? Then you can just run, you can be a bit more targeted. So those are kind of that's my favorite research, is doing these sorts of high level, how do we understand the system better work. What would you say are the biggest challenges that you faced throughout your career?
So that's a really good question. There's a lot of different challenges at different stages. I would say during university and when I first left university, and even actually in high school a little bit, I would say that having confidence in my abilities was actually quite a bit of a challenge. You have to really believe you can do it, and quiet all those voices in your head that are going, who are you to believe you can make a difference in this field, right? So that was a real challenge initially. And then I think, I have to address the elephant in the room. Like there is a big gender imbalance in both physics and engineering and both fields I work in. So, sometimes it's been challenging understanding how I can best be taken seriously, I guess is the way of saying it. I'm quite open and I have quite an open and friendly personality, and sometimes that can come across as being less professional. And when you walk into a room full of much older, more serious men, it can be difficult to, as I say, you have to kind of convince them that you can be taken seriously sometimes, and it's an unfortunate truth. It's getting better, but it's not there. It's not quite there yet. Yeah.
Okay. Well, on that note, apart from leading by example, which we're obviously doing, what do you think can be done to kind of rectify the situation of the sort of the unbalance in that respect?
I've thought about this a lot. I think that culture change is a big one, and it's not just changing the culture for women and other minority groups, like whatever that might be, but also for the many scientists that don't subscribe to this sort of more traditional adversarial kind of academic culture that can sometimes become dominant, right? So I guess what I'm trying to say is that, a culture that is dominated by people never admitting their mistakes and always only promoting other people that look and sound and act like them is not a good culture, right? Not only for the people in it, but also for the what comes out of it. You need diversity, right? So if you can start to open up that culture a little bit and get some new people in there and change that to a more open culture where you support each other, where saying the wrong thing is not a big deal, and you can actually, have thought bubbles and blurt out your big idea and without worrying that it's going to be shot down or told that you're stupid, right? So, in some ways, like these sorts of cultural changes, they help everyone. It's not just women. And what's been happening in my school here at the Australian National University is that they've had a few strategic hires, younger women and men, but with a particular sort of ethos, this ethos of collaboration and collegiality and openness. And that's really had quite a radical change over the last few years, hampered slightly by COVID, because it's difficult to change the culture through a screen. but it's, I think that's really the way to do it. And I'll just note, right, so my PhD supervisor was Professor Kylie Catchpole, so a lady. She still works at the ANU, and she continues to be a fantastic mentor. And she's been really not only this wonderful science mentor, but also someone who's been really open about how to handle challenges in academia, like work-life balance, how to handle difficult personalities or not being taken seriously. And what I find now is that in my research group, I have more than 50% women, and I constantly am attracting really good young women who want to do a PhD with me. And I'm not doing this, there's nothing I'm doing to encourage this apart from existing as a woman. So I can kind of see it in action, right? Kylie graduated me. I've already graduated one really great female scientist, Dr. Ashla Sharma. She's doing wonderful things, and I've got another couple who are just starting with me. So there's this multiplicative kind of effect if you start hiring a non-traditional people, I guess is the way to say it.
Yeah, that's a really interesting perspective on that. So it does benefit just having a better culture in that respect, and probably better for the progress of science. So, but yeah, that's really cool. So just taking a step back, a question I wanted to ask was, I know that your career has seen you travel the world a fair bit. Do you think there are any advantages to this when you're starting out? Like, how much do you feel you benefited from studying in Glasgow and Barcelona?
Yeah, that's a really good question. So I'm actually Scottish originally, and then, I grew up in Africa, moved back to Scotland to do my undergraduate, and I did my PhD in Australia. And then my first postdoc in Spain, and then back to Australia for the start of my academic career and now tenure. So I do think it helps to travel to see different cultures and to get different perspectives. So every place I've worked has had a very different, not only culture as in how people treat each other, but also approach to science. And I think, you get that if you travel between different institutes as well, but you sort of get a more extreme version if you travel to different countries or continents. That said, I think it is really important to understand the effect of that as well on your own personal life, right? So I've been very lucky. I actually met my husband in Australia during my PhD. So he traveled with me to Spain. And that's one of the reasons we came back here, is to be closer to his family. So, I've watched a lot of young scientists put their life on hold while they do the postdoc in different countries. And it can be a great experience, but, especially if you want to have a family or live in the same country as your significant other, there can be some downsides as well. And that needs to be balanced, I think. And I don't believe, while it's an advantage to travel, I don't believe that people should be sacrificing the rest of their existence, their loved ones, in order to make that happen. And I think you should be able to succeed in the we should encourage the culture that allows you to succeed while also, succeeding in other places in your life, like having a family or caring for your parents or your loved ones or whatever you want to do. So I also think that there's a lot of luck involved in getting to be an academic. There is, and all the way through a research career, you need to be good at what you do, and you need to work hard. But there's a lot of people that are good at what they do and work hard, and there's a lot of luck involved in finding the right thing at the right time, and meeting the right people to work with. Really, the right people to work with are a really important part of it. And that can happen anywhere, right? That doesn't have to happen in Spain or, some other exotic country.
On that note, looking back, is there any advice you'd like to give to your younger self, or someone who would be in a similar position to the position you were in?
That's a good question. I'm going to come back to the confidence one, because I think that's something that I struggled with a lot when I was a younger scientist. Just realizing that no one thinks that they actually know everything, and that that everyone has a small kernel of imposter syndrome. And that you just have to kind of ignore it and just give it a go. So if it's something you want to, if research is something you want to do, I just think you really have to believe that you have what it takes and go for it. So yeah, in terms of picking up the right technical skills and working hard, I've never met a student or colleague who I've had to worry about their work ethic, right? Like, forcing people to work hard is not something we have to do in science. I actually spend a lot of time trying to convince my people to take a weekend off, go home, have a good night's sleep, come back again tomorrow. So, it's more about protecting your well-being and your mental health, and, making sure that you can tackle these challenges.
Too much passion for science.
Yes.
Yeah, in terms of that, so one of the aims of this podcast is to inspire students who are potentially going to go on to research physics. A lot of the thing, as partially because a lot of the things that are covered in the A level, although interesting in many regards, are things that we've known for over 100 years at the earliest. So to kind of showcase the sort of things that they could go on and research and get them excited about, going off and, I mean, trying to save the world like you're doing in developing renewable energy. Is there anything that you think would be really cool to add to the sort of school curriculum that you would have found really interesting about?
This is purely because I work in this, right? But I do think that understanding where we get our energy and how we use energy and the complexity of the energy system, I think that would be a really interesting, segue somewhere in the physics curriculum. But also, I think trying to just break down those barriers between fields a little bit more, right? Understanding that you can't do physics. I was going to say you can't do physics in a vacuum, but usually, we assume we're in a vacuum and everything's spherical, and you can't have a big impact in physics in a vacuum. You have to understand the context, and you have to do a lot of this really careful problem finding to understand what's the real problem that you need to solve. So it'd be good to try and showcase that a little bit in high school. So recognize you don't have to pick a lane, right? You don't have to just be a physicist or just do an arts degree. You can actually solve some or you have a lot to add as a physicist into all of these policy questions, and vice versa. The policy people have a lot to tell us about what the real sticking points are. So I don't actually know how that would work, but if someone could figure it out, that would be great. Yeah.
No, that's insightful. That definitely is. That would be useful. It does seem like no one ever ends up doing just a very narrow thing, or very few people end up having a career which is completely narrow. Or at least hopefully it seems more interesting to have some diversity within that.
Well, I've definitely found so. Yeah, that's true.
How do you go about trying to solve problems?
That's a good question. And actually, even after all these years, there does seem to still be a bit of my process that is not quite a conscious process. There's the things you do, like reading and making space for thinking, which is actually harder than you would expect. But that really deep intellectual work, while it's really interesting, can be quite hard, right? It's much easier just to check your emails and do some administration tasks if you're not quite in the mood. So making sure that you're giving yourself the right amount of time. And as I said, I quite like to make these models, right? So if I'm faced with a new type of system or a new area, I quite like to start by just opening MATLAB and making myself some simple little analytical models based on the physics we already know and plotting things against each other. So I'm a very visual person, so I like to look at the data and understand the data a little bit and look at different ways of visualizing it. To pick out, how things change and essentially, usually it's been a couple of times when I've started doing that just to understand the system more generally, it's led to some really interesting research questions that have gone on to be quite a significant part of my research. So I guess that's not quite an answer to your question, because I'm also talking about problem finding in there. And I've used that term already, but I mean, problem finding is actually almost more important than solving problems, because finding the right problem to solve is really the first part of it. So, as physicists, we're trained very effectively to solve problems and to think about things logically and explore all the options. But we're not quite trained. At least I wasn't when I went through my degree, quite a while ago now. But that, understanding how to actually, what is the most important problem to solve and this is something actually we teach engineering students. I'm teaching this first year engineering course, and this is something we teach as part of the engineering process is this problem definition. I really like this concept, right? The statement of the problem that you come across might not actually be the best way of thinking about it. You need to actually figure out what the real crux of the issue is and that can be quite an intellectual exercise as well, and involves quite a lot of research and analysis.
What does that tend to look like? How do you go about trying to find the right problem?
Depends what you're looking at. So if it's so I'll give you two examples, one very technical and one not. So if you have a device, so let's say you have your solar hydrogen generation device and it's not working very well. And why? What's the problem? So you have to run a bunch of experiments to start narrowing that down. We also use models again, sort of saying, okay, how is this behavior different to the analytical model? And how does that allow us to pick out what's the issue here? Is it the context? Is it something in the material that is not quite, that shouldn't be there? Or and so you can, figure out that problem, what the actual problem is, and before you go and solve it. In the sort of big picture energy space, the question might be, how do we start making renewable hydrogen in Australia and export that instead of natural gas? Well, that's such a what's the actual problem there? We could do that. I could buy an electrolyzer and some solar panels and make some hydrogen and put it on a ship and send it to any other country I want. But that's not that, so it's not necessarily that we can't physically do it. It's that it's complicated and it's expensive and we don't have the regulations yet. So you have to start understanding the status quo very well before you figure out what is the real barrier to what you're trying to do. You also have to talk to a lot of people. So, talking to government officials, talking to industry, the people who would be buying or selling or moving the hydrogen around. So there's a lot of consultation that needs to happen before you get to the point where you go, all right, what we need to do? We need to work on certification, for example. That's going to be the thing that allows a renewable market to grow. So yeah, two different examples, but both start with this need for more information before you actually zoom into what problem you're trying to solve.
In terms of that, in terms of the problem definition, I guess the question would be, what are your thoughts about the other potential forms of renewable energy? So, for instance, nuclear fusion, which has had a recent burst of excitement. How do you go about finding the right avenue to follow in the first place?
Yeah, that's in terms of where you, as a person, as a scientist, want to put your energy. I think you need to follow your passion, right? As I said, I was. I don't know if I did say actually, but when I was at university, I was very, very interested by solid state physics and materials. So that kind of led, and optics as well, right? Which is, and how light interacts with matter, which is, part of the solid state physics area, really. And that really, or strengthened my interest in solar energy. Wind is a fantastic other form of renewable energy, but I'm just not that excited about big rotating engines. I can't quite get passionate about that. And likewise with nuclear fusion and fission, that it's not quite what I'm interested in. I actually see the end state for us, for our energy system, is not one that's necessarily dominated by any one technology, I think. We're going to need wind and solar. I mean, I think they're going to play a very big role just because they're, especially in the near term, because they're already being, rolling out. But if we could get fusion to work, and if we can get it to work in, economically, then that could be a really big game changer for us. And that would be fantastic. It would take away a lot of the issues that we're seeing now with wind and solar variability and how that affects the grid and the need for batteries and things like that. So and likewise, if we can figure out how we deal with the issues, including the political and social license around nuclear energy in its existing forms, right? And then, you know, that could potentially play a role as well. But you know, as it is in its current state, I can't see it ever really being a major part of the solution, because nobody wants it in their country. So, yeah. I don't know if that answered your question, actually.
No, that answered it. That's, yeah. So I guess if you were to work on anything else in the future, what do you think it would be along the avenue of potentially something else to plasmonics? I know you're passionate about that, but what would be a future project that would excite you?
Yeah, I'm getting very interested in this carbon dioxide drawdown. So I mean, we're doing some experiments in the lab where, you know, we're actually just looking to see if we can do it with our structures. But I'd like to start thinking more broadly about how we achieve this on the really large scale, because a lot of the climate modeling has shown that we're going to need to actively draw carbon dioxide out of the atmosphere if we want to, you know, stay on the 1.5 degree warming scenario that we need to do if we want to avoid the most catastrophic effects of climate change. So I'm quite interested to understand what that looks like. So the ideal would be to be able to, you know, change carbon dioxide in the atmosphere to something that's inert and useful, you know. So one of the things would be, you know, can we change it to another form of carbon, like graphene, for example, or graphite, which could be used in a way that isn't going to release the carbon dioxide later on. So these are the sorts of things that problems that I'm interested in facing. In terms of the science, though, what we're finding is that because these plasmonic structures have such finely tunable optical properties, well, we're really interested to see if we can convert that into what we call selectivity of reactions. So one of the things that is an issue in chemistry is that you might want to turn your reactants into product A, but they can also turn into product B, C, D, and E. And if they do that, then that's you really don't want those products. So there's different ways to try and force them into the right product, but we're interested to see if we can use these really intricate optical properties of these nanostructures to really select which one of those reactions we do. So that's sort of near-term goals. We're still trying to work out how we tackle that. So maybe if you talk to me in a few years, I can tell you more about that.
It would be cool to do a follow-up interview in a few years. Just checking how much time we have left, sorry. Okay, so what idea in the history of science do you think was the most revolutionary? Just getting on some broader questions.
That's a hard one. That's a really hard one. What idea revolutionary?
It is a big question.
It's really difficult to start thinking about, right?
Yeah.
Because, like, you know, it's got to be this whole understanding of quantum behavior, right? This understanding that the atom is not this. It's not a pudding. It's a mini galaxy, right? You have distinct. Yeah, it's a distinct, the fact that you have distinct energy levels. I mean, that is insane. I don't. Every time I used to teach a semiconductor course, and I just used to every time I reviewed my notes to teach it, it's like, we don't wonder at this enough, that this is the way it works, and the vast number of applications that this has allowed us, including things like solar cells and lasers and diodes and all sorts photodiodes and all sorts of things. Well, diodes in general, actually. So it's it's allowed us to do so many complicated and fundamental applications for our society. And yet the idea is really quite, it's difficult to understand how you make that leap, right? Yeah.
I agree with that. Yeah, it's difficult to conceptualize. But yeah. Is it surprising on a similar note, I guess, that we're able to model our universe so well using mathematical tools, even when it appears pretty non-intuitive?
Definitely. So I have much more experience modeling the very small limits rather than the very big, which I leave for the cosmologists. But the fact that, so we've been doing some density functional theory calculations, which is essentially using numerical methods to work out all the possible energy levels in a collection of molecules and where electrons could be. And that blows my mind every time. And at the same time, it's we are able to do this, but we're still, even with, we've got the nation's supercomputer here at the ANU, and it's fantastic. But even with the big supercomputer, we can still only do, a handful of molecules. And even that is quite amazing. So the sheer complexity and the amount of information that's stored in the smallest amount of matter is just quite remarkable.
Yeah, that is, that is amazing to think about. Okay, so as I think we are running out of time, just on a final note, I know you've already said that confidence is a big thing, and trying to, like you said, a lot of people feel imposter syndrome, and making sure that you have the confidence that you can make a difference. Is there any final piece of advice in addition to that for up and coming scientists that you'd like to share before we finish?
Yeah, I think that following what you're really interested in and really passionate about is more important than trying to be very strategic in working out exactly which area you want to be working in, right? So do what you want at high school, do what you're interested in, because you'll do it well. And likewise in high school, in university, do the courses you're really interested in. Don't worry too much about molding your courses to fit some imaginary career you think you're going to have, right? Because there's a lot of learning that goes on after you get your degree, and where you end up is going to be determined by a whole range of factors, none of which you necessarily know about right now. So enjoy it. Just, do what you find interesting, because that'll get the best results for you, and trust that opportunities will arise, and you'll always, as a physicist, you're going to be in a fantastic position to work in a range of industries in science and outside of science as well. So just enjoy the process, and don't worry too much about where it's leading.
That's really good advice. Thank you so much for spending your valuable time doing this with me today. It's
no
really
worries. It's great work. Really great initiative. 100% support it. Well, good luck with everything, Casper. I'm sure whatever you end up doing, you'll do it very well.
Isn't she great? I do hope that one day I'll get the opportunity to interview Dr. Beck again and see how much further her important work has progressed. Thank you for tuning in and for your continued support. I'll be focusing on my A-levels from now until June, but I have lots more interviews lined up from July, so please remember, like, share, comment and subscribe, and I look forward to seeing you next time.